So to think about why we don't need to worry about angular acceleration, I'd like us to go back to this top-down view of the Earth's orbit. We've said here that it takes 365 and a quarter days for the Earth to complete that orbit. Now, that's telling you that the angular velocity isn't changing. The rate at which the angle that the Earth's at is changing with time is a constant. If it weren't a constant, then the years would be either getting longer and shorter. Now we know, in fact, that there is a small change in that, but in human time scales, it's negligible. And with a lot of the problems that we look at in circular motion, they very closely approximate to a constant angular velocity. So, in other words, the time taken for each orbit to be completed won't change. And you will not be asked and you will not be required to solve a problem at A level which has an angular acceleration. In other words, the way this orbit is going, it's always going to be the same time taken to go through the same angle. So this brings us quite neatly on to our next definition. And this is the definition of uniform circular motion. And just as we saw right back in our first example, that when we had uniform acceleration, we meant the acceleration was constant, it wasn't changing. With uniform circular motion, this is circular motion with a constant angular velocity, a constant omega. And that effectively means that we can forget about angular acceleration. The reason why we can forget about angular acceleration is because it's zero. So uniform circular motion is circular motion with a constant angular velocity. And that allows us to derive some formula that on your formula sheet, which are quite important for this. So if we then look at this idea of time period, this is, I suppose, another definition. This is going to be the time taken to complete one circle, in this case, one orbit. Now, we can find the equation for that in a relatively straightforward way. So we know that omega, the angular velocity, is equal to the change in angle, delta theta, divided by the change in time. Now, if we're looking at the time taken to complete one circle, we're effectively looking at the time in which the Earth's orbit example has done one orbit, so 1 year's worth of motion. What is our change of angle going to be in this case? One circle is 2 pi radians, and we said, we know in this case our time period is 365 and a quarter days. Our time period in the formula is given the letter t for any time period, so we end up with omega equals 2 pi over t. This is the next one of your key results, and on your formula sheet, but it's good to know, have off the top of your head the clear link between the angular velocity, how much the angle is changing with time, with the time period, the time taken to complete one orbit. There's another very closely linked definition, which is the frequency. And you've come across frequency at GCSE with waves. It's the number of waves per second. In circular motion, it is the number of full orbits completed in 1 second. With this, you know it's going to be a very small fraction of a second because it takes the Earth so long to complete one orbit, but that won't be the case for a lot of the problems that we look at. So we've got the number of full orbits completed in 1 second. It's given the letter small f. We've seen at GCSE there's a very simple formula, f equals 1 over t. Substitute that into the formula we've had above, and you end up with omega equals 2 pi f. Another formula which you need to have off the top of your head by towards the end of next year, if you're needing to look at a formula sheet to remember these two formula, you're going to be restricted with marks. There's a huge time pressure in the exam, and these are formula that even though are given to you, it's expected, or I'd expect you to be able to recall them quickly off the top of your head rather than having to spend time looking through your formula sheet. So just to recap, 2 or 3 here really important definitions. We look at uniform circular motion because a lot of problems the angular velocity doesn't change, and because of that we can introduce 2 more definitions: the time period, the time taken to complete one orbit or one circle, and the frequency is the number of full orbits completed in 1 second. And there's 2 simple equations there linking the time period and the frequency to the angular velocity. In other words, when you've got the time period or the frequency of an orbit or something in circular motion at a constant angular velocity, you can straight away go and calculate this angular velocity there.